Welcome to our deep dive on protactinium. You wanted to understand more about this element, and the sources you sent over: history of protactinium, some Wikipedia articles, and a research paper about its applications.
Those seem like a really good place to start.
Yeah, they do.
Yeah.
So let's try to uncover what makes protactinium so intriguing.
Well, it's pretty interesting that even before scientists were able to isolate protactinium, its existence had been predicted.
Really?
Yeah, Dmitry Mendeleev, the guy who created the periodic table,
Right.
he anticipated its presence back in 1871.
Wow, so he knew there had to be an element between thorium and uranium, even though nobody had ever seen it.
Exactly, and he even gave it a temporary name, eka-tantalum, thinking that it would resemble tantalum in its properties.
Eka-tantalum.
Yeah.
Oh, so that sent chemists looking for an element that behaved like tantalum?
Right, and that wasn't really the right approach.
It wasn't.
No, it wasn't really until the discovery of dubnium, the true heavier counterpart to tantalum, that the real puzzle piece slotted into place.
I see. So focusing on tantalum was a little bit misleading then.
Right. Kind of led them astray.
Okay, so when did scientists actually get their first look at protactinium?
The initial discovery was in 1913 by Casimir Fijans and Oswald Helmuth Goering.
Okay.
And the isotope that they discovered, protactinium 234 meter, had a very short existence, a half-life of just 1.17 minutes, so they actually named it brevium.
Brevium, meaning brief, I guess. It was
Yeah.
just a quick little blip. But then, just a few years later,
Yeah.
two separate groups of scientists, Lise Meitner and Otto Hahn in Germany, and Frederick Soddy and John Cranston in Great Britain, they found a much longer-lived isotope.
Yeah, protactinium 231.
Okay, and that was a pretty big deal, right?
Oh yeah, this discovery was a game changer. It really allowed us to understand protactinium better and also led to the name protactinium, literally the nuclear precursor of actinium, because it decays into actinium.
Oh, that makes sense. So we have Mendeleev's prediction, then a brief appearance of brevium, and finally the discovery of protactinium-231. What happens next in this protactinium story?
Well, isolating protactinium in its pure elemental form was quite a scientific feat.
I bet.
It wasn't until 1934 that Erstedt von Grosse was able to accomplish this, and he had to use a really complex technique.
It sounds complicated. Can you tell us a little bit more about what von Grosse did?
Sure, he used a method known as the Van Arkel de Boer process,
Okay.
which involves converting protactinium oxide into a halide, like a chloride or bromide,
Okay.
and then you heat that in a vacuum using an electrically heated filament, and this causes the halide to decompose, depositing pure protactinium metal onto the filament.
Wow, so protactinium finally gets isolated. So where does it fit into the whole scheme of the periodic table?
Protactinium is part of the actinide series, and it's right between thorium and uranium.
Okay.
A lot of its physical characteristics, as you might expect, are kind of in between those two elements.
So what's protactinium like in its pure form then?
It's a dense, silvery gray metal.
Mm-hmm.
It's heavier and more rigid than thorium, but not as dense as uranium. Even its melting point is somewhere between the two. And its thermal and electrical conductivity are pretty similar to other post-transition metals.
So its properties seem to kind of follow the trends of its neighbors.
Yeah, it's pretty neat.
That's really neat. Our sources mention that protactinium is pretty rare,
Yeah.
even though it's sitting right between two fairly common elements.
Right.
Why is that?
So it's true that protactinium forms from the decay of uranium.
Okay.
But its most stable isotope, protactinium-231, has a half-life of over 32,000 years,
Okay.
which may sound like a long time,
Yeah.
but it's actually relatively short in geological terms.
Oh, okay.
Most of the protactinium that was present when the Earth was formed has already decayed away.
So what we see today is just a tiny, tiny fraction of what was once here.
Exactly. It's a case of here today, gone tomorrow on a geological timescale.
And the protactinium we do find, where is that?
It mostly occurs in uranium ores like pitchblende.
Okay.
But even then, the concentration is incredibly low, just a few parts per million.
Wow. So if it's that rare, how do scientists even get enough of it to study it?
Well, for a long time, they really only could extract it from uranium ores,
Okay.
which is a very difficult and expensive process.
Yeah.
But luckily, another source has emerged: spent nuclear fuel.
Spent nuclear fuel. I wouldn't have thought of that.
Yeah, certain types of nuclear reactors, especially those that use thorium as fuel, produce protactinium as a byproduct.
Interesting.
And in fact, two main protactinium isotopes, 231Pa and 233Pa, show up in these reactors, although they're often considered undesirable and are actually removed.
So it's rare and it's a bit of a nuisance in these reactors.
Yeah, pretty much.
I guess that explains why it's not used more widely.
Exactly. It's the scarcity, the radioactivity, and the toxicity.
Right.
All of those things really limit its practical applications and confine it mostly to research.
So if it's not useful in the usual sense, why do scientists even bother studying it? What makes it so interesting to them?
Well, that's where things get really exciting. Protactinium may not have conventional uses, but it actually holds incredible potential for uncovering secrets of the Earth's history.
Okay, you've got to tell me more about that. This is fascinating.
Protactinium-231, the isotope with that long half-life we talked about,
Right.
is a bit of a time traveler,
Okay.
and scientists use it like a clock to date marine sediments, which allows them to look back in time as far as 175,000 years.
175,000 years.
Yeah.
How does this protactinium dating method actually work?
It's all about the ratio of protactinium-231 to thorium-230 in sediment layers.
Okay.
Both of these isotopes originate from the decay of uranium, but they accumulate in sediments at different rates.
Right.
By analyzing their relative concentrations, scientists can actually pinpoint how long ago that sediment was deposited.
So just by measuring these ratios, they can actually create like a timeline for these sediments.
Exactly. And by studying the distribution of protactinium in these different sediment layers, we can figure out what ancient ocean circulation patterns looked like.
Wow.
It's like piecing together a puzzle of the Earth's past.
That's pretty remarkable. So it helps us understand how our climate has changed over time.
Right.
And it's not just limited to oceans, right?
Right. This dating technique can actually be applied to a lot of different geological processes, like the formation of mineral deposits.
It's like a really useful tool for geologists then.
Exactly.
It's amazing how an element with no obvious practical uses can be so valuable scientifically.
It shows the power of research and how even seemingly insignificant elements can have really surprising applications.
Before we get too far into the science,
Yeah.
I think we should talk about the fact that protactinium is highly radioactive and needs to be handled very carefully.
That's a really important point.
Yeah.
Protactinium's radioactivity is definitely a double-edged sword. It's incredibly useful for scientific dating, but it also poses some pretty significant health risks if it's not handled properly.
So what are the main dangers associated with protactinium exposure?
Well, protactinium-231, the isotope that's most often used, mainly emits alpha particles. And alpha particles are pretty heavy, and they don't travel very far in air.
Okay,
Even a sheet of paper or your skin can stop them.
that's good.
So
Yeah.
the biggest risk with protactinium is really from internal exposure.
Okay.
Like if you ingest it or inhale it,
Right.
if that protactinium-231 gets inside your body, those alpha particles can cause a lot of damage to the tissues and organs around it.
Right, and you said that it tends to accumulate in the bones.
Yeah.
What happens then?
Well, if it's incorporated into bone tissue, the alpha particles that are emitted can actually damage the bone marrow, which can lead to some pretty serious long-term health problems like bone cancer.
So we really, really want to prevent any internal exposure then.
Exactly.
But didn't you also say that its decay products can be even more dangerous?
That's right. It's really important to remember that. Actinium-227, the decay product of protactinium-231, is actually a lot more radioactive than its parent isotope.
Okay.
And it emits both alpha and beta particles, which makes it a lot more difficult to shield against them.
Right, and it also has a shorter half-life, right? So it
Yeah.
decays more rapidly.
Exactly. So even though we start off with protactinium-231, which is sort of mild,
Uh-huh.
over time, that decay process leads to a much more potent radioactive mixture.
So how do scientists make sure they're being safe when working with protactinium?
It takes a multifaceted approach, addressing both the element itself and the decay products.
Okay.
And it really starts with minimizing exposure.
Right.
Protactinium usually handled in sealed glove boxes
Okay.
that are filled with an inert gas, like argon, to prevent any reaction with air or moisture.
Oh, so like those things you see in sci-fi movies, the researchers working with the glowing substances.
Something like that, yeah.
I see.
These glove boxes are designed to really contain that protactinium and prevent any accidental release. And researchers wear all sorts of special protective gear, gloves, respirators, things like that,
Okay.
to reduce the risk of exposure even further.
So they're being as careful as possible to make sure that they're safe and that the environment is safe as well.
Absolutely. And research is always going on to develop even safer and more efficient ways to handle protactinium.
Oh, really?
Yeah, for example, scientists are exploring the use of molten salts and liquid metals as solvents,
Interesting.
which could make extraction and processing easier and also minimize the risk of contamination.
So it's constant effort to improve safety then.
Exactly. As we learn more about protactinium and how it behaves, we can adapt our methods to make sure that we're handling these powerful materials responsibly.
Makes sense.
Welcome back to our protactinium deep dive.
It's amazing how one element can have so many things to discover about it.
It really is, you're right.
Yeah.
There's a lot more to protactinium than meets the eye.
Okay.
For instance, we talked a little about its role in dating marine sediments.
Right.
But it's actually used in a lot more areas of geochronology than that.
Really?
Yeah, and remember how we mentioned protactinium-231 is mostly found in uranium ores?
Yes, like pitch blende.
Right, well, the ratio of protactinium-231 to uranium in those ores can actually tell us a lot about their history.
Okay, I'm all ears.
So let's say you have a sample of uranium ore. As time passes, that uranium decays and protactinium-231 start to build up.
Okay.
And if the ore is left alone, that ratio of protactinium to uranium eventually reaches a state of equilibrium.
Right, so it's like a balance between the decay of the uranium and the formation of the protactinium.
Exactly, but here's where it gets kind of interesting. If that ore is disrupted, like by some geological process, weathering or maybe groundwater flow,
Okay.
that equilibrium gets thrown off.
So if scientists analyze this ratio, they can see if an ore deposit has experienced some kind of geological disturbance.
Exactly. It's like a detective looking for clues.
Right.
The protactinium to uranium ratio can tell you about events in the past that might have changed the ore.
That's really cool. Like, these little radioactive atoms hold so much information about the Earth's history.
It is pretty amazing.
It is.
And it's not just about dating ores. This technique can also be used to look at how radioactive elements move around in the environment.
That sounds important.
It is. Understanding how those elements move through soil and groundwater.
Right.
That's really important for things like managing nuclear waste disposal and environmental remediation.
Yeah, because we don't want those radioactive elements ending up where they shouldn't be.
Exactly.
So protactinium can help prevent that.
Well, in a way, yes.
Oh.
Protactinium-231, with its long half-life and unique chemical behavior.
Right.
It makes a really great tracer for studying these processes.
I see.
And by tracking how it moves,
Right.
we can get a better understanding of how radioactive contamination spreads, and then use that knowledge to develop effective strategies for containment and cleanup.
So it's helping us make better decisions about nuclear waste and environmental cleanup.
Yeah, pretty much.
It's really cool how such a, seemingly obscure element
Yeah.
can have such important real-world applications.
It really highlights how interconnected science is, and how even these unexpected discoveries can help us address some big global challenges.
Right.
But we've really only just touched the surface of protactinium's potential.
Okay.
Remember those other protactinium isotopes that we find in nuclear reactors?
You mentioned protactinium-233, I think, being a bit of a nuisance in thorium-based reactors.
That's right. Well, it turns out that this nuisance actually has some interesting properties that scientists are starting to investigate.
Okay, like what's so special about protactinium-233?
Well, for one thing, it decays into uranium-233,
Okay.
which is a fissile isotope.
Fissile, does that mean it can sustain a nuclear chain reaction?
That's exactly what it means.
So are you saying that protactinium-233 could maybe be used as a fuel source?
It's possible, but it's not quite that simple.
Okay.
Remember, protactinium-233 is an intermediate product in the thorium fuel cycle. It's not something we just find lying around in nature.
So we'd have to produce it in a reactor first.
Exactly.
But if that process could be made efficient, then protactinium-233 could be a really valuable fuel source, especially with all the interest in thorium as a safer and more sustainable alternative to uranium.
You're getting it. There's a lot of research being done right now on how to optimize the thorium fuel cycle.
Right.
And protactinium-233 plays a big part in that.
Okay.
There are some challenges, though.
Like what kind of challenges are we talking about?
One of the big ones is figuring out how to extract it efficiently from the reactor core.
Right, because it's highly radioactive.
Right, so that's going to require some really specialized techniques and careful handling.
Right.
And then another challenge is managing the decay of protactinium-233 into uranium-233,
Okay.
which generates a lot of heat.
It sounds complicated.
It is. There are a lot of things to consider,
Yeah.
but the potential benefits are pretty huge.
Yeah, that's true.
That's what's driving all the research.
I see.
Protactinium-233 could really be a game changer when it comes to finding clean and sustainable energy.
Yeah.
It's pretty amazing to think that this element, which was pretty much unknown for a long time,
Right.
could actually hold the key to a better future.
That's really inspiring to see how scientific curiosity can lead to such amazing possibilities.
Yeah, it is.
But I understand there's even more to the protactinium story.
Right.
What other potential applications are scientists looking into?
Well, Protactinium-233 also shows some promise in the fields of medical imaging and cancer therapy.
Wait, are we talking about using a radioactive element for medical purposes?
We are.
Isn't that dangerous?
It can be, but it's all about using that radioactivity in a controlled and targeted way.
Okay.
You see, Protactinium-233 decays by emitting beta particles, which are high-energy electrons.
Right.
And these particles can be directed to actually destroy cancerous cells while minimizing damage to the surrounding healthy tissue.
So it's like a tiny little weapon,
Yeah.
delivering a precise dose of radiation to get rid of tumors.
You got it.
That's amazing.
Now, this is still very early-stage research, but the potential benefits are pretty significant.
Wow, so we've gone from protactinium as this time traveler to protactinium as a potential energy source, and now we're talking about protactinium in medicine.
It's been quite a journey.
It really has. It's amazing.
It really shows how connected all of science is,
Uh-huh.
and how even the most unexpected discoveries can lead to really revolutionary applications.
Welcome back. We've learned so much about protactinium already, from its origins to its potential to change energy and medicine.
It really is a testament to how scientific curiosity can lead to some amazing and unexpected things.
Exactly, but let's not forget that working with protactinium means we have to be aware of its radioactivity
Right.
and the risks that come with it.
Safety has to be the top priority.
Okay, so let's focus on that for a bit. What are the main risks when it comes to protactinium exposure?
Well, as we've talked about before, Protactinium-231 mostly emits alpha particles.
Right.
And those are pretty heavy and don't travel very far. Yeah. Even a sheet of paper or your skin can block them.
So I'm guessing the biggest danger then is if it gets inside the body.
That's exactly right. The most significant risk is from internal exposure.
Okay.
If it gets in through ingestion or inhalation, those alpha particles can really damage your tissues and organs.
You mentioned that protactinium tends to accumulate in the bones.
Yeah.
What happens then?
Well, if it gets into the bone tissue, the alpha particles can actually damage the bone marrow,
Right.
which can lead to long-term health issues, things like bone cancer.
Definitely.
So we really have to make sure that doesn't happen.
Definitely.
But what about its decay products? You mentioned that those could be even more of a problem, right?
Yes, it's a really crucial thing to remember.
Okay.
Actinium-227, what protactinium-231 decays into, is a lot more radioactive
Oh, okay.
than its parent isotope, and it emits both alpha and beta particles.
Which makes it harder to block.
Right, exactly. And it also has a much shorter half-life.
Right, so it decays faster.
And releases more radiation more intensely.
Yeah.
So how do scientists work safely with protactinium, given all of this?
Well, they take a multi-pronged approach,
Okay.
addressing the protactinium itself and its decay products, and it all starts with minimizing exposure.
Right.
So protactinium is usually handled in those sealed glove boxes,
Okay.
the ones filled with an inert gas like argon.
Right, to keep it from reacting with the air.
Right, exactly.
It's like those sci-fi movies with the researchers working with those glowing things.
Yeah, pretty similar.
Very cool.
So these glove boxes are made to contain the protactinium,
Okay.
so nothing gets released accidentally. And researchers wear all that special gear, gloves, respirators.
Right, to protect themselves.
Exactly.
So they're taking every precaution then.
Absolutely. And they're always researching ways to make it even safer
Oh.
and more efficient to handle.
Like what? What are they working on?
Well, for instance, using molten salts and liquid metals as solvents.
Interesting.
That could make extraction and processing a lot simpler and reduce the risk of contamination too.
So it sounds like it's a continuous process of improving safety.
That's right. As we learn more about protactinium, we can adapt and make sure we're handling this material responsibly.
Well, this has been an incredible deep dive.
It really has.
We've gone from protactinium's discovery and its properties to its potential in energy and medicine.
Right. And even touched on the importance of safety.
It's clear that protactinium has a fascinating story,
Absolutely.
and we've only just scratched the surface.
There's still so much more to learn and discover.
Protactinium shows us how important scientific research is.
Yeah.
And it also reminds us that we need to be responsible with these discoveries.
Exactly. Progress and responsibility have to go hand in hand.
So thanks for joining us on this journey.
It's been a pleasure.
And keep exploring the amazing world of science